Hello all, welcome to operating system course. So yesterday we had seen about the structure of the page table, right? So today we'll get started with the segmentation topic. Okay. So the important aspect of memory management that became unavoidable with the paging is the separation of your user's view of the memory from the actual physical memory. So we have seen, right, how the physical memory is divided into frames and how the logical space or the logical memory is divided into pages, or the process is divided into pages, right? So that user's view of the memory, it is not the same as the actual physical memory. So the users will, what we see is mapped onto the physical memory. That means whatever the partitions that are made, that are there in the secondary memory, that is the pages, those are mapped onto your physical memory. So this mapping, it allows the differentiation between your logical memory and the physical memory. Okay. So what is segmentation, why this is needed? So this segmentation, again, it comes under your non-contiguous memory allocation. So basically what the user think. So as a user, we think that memory as a linear array of bytes, some containing instructions and others containing the data, right? So most people would say no, it is not like that. But users, they prefer to view the memory as a collection of variable size fragments with no necessary ordering among the segments, like basically like this, right? So this is the user's view of program. So say suppose what we had thought of previously. So if we had written C program, so in the secondary memory you would have thought that, like, so suppose say for example we have say factorial.c. Okay. So we have factorial.c program, whichever you have written, and you have saved that, right? So this is in your secondary memory. So what we thought is like, so this factorial.c, which is our process, it would be divided into multiple equal sized partitions, and each partitions we call it as a page, right? So in that page, what we'll have, some instructions will be present of your factorial.c. Say suppose here um, say suppose 5 instructions are present here, 10 instructions are present, something like that we had seen, right? But actually how a user view, or he tries, or he prefers to view a program is something like this one. So this is your logical address. So in the logical address, the user thinks or prefers to see the program like this. Suppose if you have factorial.c, you have say a main program. So you have written a main function, right? And in main you have written some lines, and then say suppose you have written a factorial function separately, right? So that, again, this will be present in your program itself. But how it is saved is like main memory as one segment, right? Your function is of another segment. Say suppose your program contains some data structures like stack, it would be kept in another segment. If you have a square root function, definition of the square root function, it will be kept as a block or the segment in another part. If you have symbol table, it would be kept in another part. Basically, your program is divided into multiple parts such that main function is kept somewhere, square root function is kept somewhere, some other function is kept in another way. But it would be like in a block or the segments. Now you have to understand here, these segments are of different sizes. It will not be of same size. Okay. Basically, the length of these segments are defined by the purpose of that particular segment. That means if, say suppose you have a factorial function, what is the purpose of factorial function? It is to calculate the factorial, right? The length depends on that particular uh, purpose of the function. So elements within the segment, these are identified by their offset from the beginning of the statement. If suppose I take this as say suppose this is the square root function, right? So this square root function, it will have multiple instructions, or the code whatever you have written for the calculation of the square root. Then say suppose if you want to access any one particular instructions inside this segment, how can you do this? Is by using offset. Okay. Offset or displacement, we know the meaning of offset or the displacement, right? It is the actual location of an instruction within this segment. So these are the segments, right? segment 0, segment 1, 2, segment 3, and segment 4. So the program is divided into 5 segments, and if you want to take a particular instruction, you want to execute the instruction, so that how can you find out is by the offset. Then how do you find out? Okay, if suppose this starts from location 0 till, say, suppose this is 50th location, and now if you want to execute this instruction, what you have to do, you have to add the base address of this particular segment, that is 0, with the displacement or the actual location. So 0 plus 50, it is 50, right? So that means in the 50th location your actual instruction would be present. Okay, so basically segmentation, it is a memory management scheme that supports this particular user's view of memory. That means your logical address space, it is a collection of segments. So each segment will have its name as well as the length. Okay, so the addresses specify both the segment and the name, segment and the offset within that particular segment. So the user, therefore, he has to specify the address with the two quantities. If I want to access this main program, then how can you access this main program or this particular segment is by its name as well as the offset. So basically name is, we can have duplicate names. Therefore we use something called as segment number. That would be unique number whichever that would be given to your segments. Fine. So each logical address, it consists of two tuples, we say, or basically two parts. One is segment number, another one is offset. Okay, like segment number, if suppose this is 01, 02, 03, something like this, then if I want to access this particular segment's, say, fifth instruction, then what has to be done is like I have to give this name or the number basically. Okay, this is the segment number and this is the offset. Then the user program is compiled, and the compiler automatically it constructs these segments reflecting in your input program. Say suppose you have a C compiler, then how a C compiler it would create separate segments is like, for code it will create some separate segment. Okay, say suppose in the factorial.c, let's take this example. So you have to compile this one, right? Now how your C compiler will create the segments? Say suppose for the entire program, entire code, whatever you have written in the logical address space, say suppose you have one segment. This is only for the code. Okay, say suppose this is first segment, or say 0th segment. Then if you have any global variables that are declared in your program, then that all the global variables would be in a separate segment, say segment number 1. Then if you have heap from which the memory is allocated, that would be another segment. Then if you have stacks that are used for for your processes, then that could be another segment. The last one is for your libraries, like stdio.h, then math.h. For those libraries, that would be another segment. So this, like, five, your C compiler would create or divide the program into these 5 segments. Okay, so this is the basic understanding of your segmentation. So it is nothing but your program is divided into multiple segments. In paging, what we did, we divided that particular process or the program into fixed size partitions that are called as pages, right? But here what we are doing, the same program, whatever you store, it will be divided into multiple parts, and that parts we call it as segments, and these segments will be of variable length. Okay, the length of each segment, it defines or it depends on the purpose of that particular segment. Fine. Now we will see the hardware here. Okay, hardware, or basically the segmentation hardware. So what will happen is, whenever the CPU it generates the logical address, it is divided into two parts. One is your segment number and another one is your offset or the displacement. In paging, what happened? In paging we did, whenever the CPU generated logical address, it was divided into two parts. One is page number, another one is your segment. Here instead of page number we have the segment number. Fine. Now next process is, this segment number is given as an input to segment table. Now what does this segment table contains? So segment table, it contains it contains index as the segment number. Okay, so suppose if this is your logical address space, say we have consider these three as the segments. Okay, so say suppose this is first segment, second segment, and the third segment. Then this segment table would have the index as the segment numbers, like segment number 1, segment 2, segment 3. Like these are the numbers, segment numbers are the index to your segment table. Fine. Then it actual contents of the segment table is limit and base. Fine. Now what is limit and base? So limit is nothing but, okay, first I'll talk about the base. Okay, so base is nothing but starting address of your segment. Okay, so say suppose this segment 1 is stored in your physical memory. Okay, I'll draw here. If this is your main memory, okay, say suppose your segment 1 is present here, and the base address is 1000, and this is the end point is, or end location is 1500. This is for assumption. Okay, now your base is nothing but the base address of that particular segment in the main memory. So this segment 1, it is present in the main memory at the starting location 1000. So this 1000 becomes the base address for your segment 1. Okay, now here base, it contains the value, say suppose 1000. Now what is limit? Limit is the range of this particular segment. Say suppose 1500 minus 1000, that is 500, right? So this limit is nothing but the value 500. So I'll repeat once again. Segment table, it will have the segment number as the index, and it contains two quantities or parts, that is limit and base. Base is nothing but the starting address of that particular segment in the main memory, and limit is nothing but the actual size or the limit range of that particular segment in the main memory. Okay, so I'll come back to this diagram now. So whenever the CPU generates logical address, it is divided into two parts, segment number and displacement. The segment number is searched in the segment table, and from the segment table, if suppose there is a match, you got that particular index or the segment number, you first take the limit of that. What is the limit, right, of that particular segment in the main memory? You extract that, and then what you do, you compare this limit with the displacement or the offset. If suppose the displacement or the offset, that is the actual location of the instruction in the main memory, if it is less than the limit, okay, if it is less than the limit means you are trying to access the instruction between 1000 to 1500, which is a valid one. So if you are doing that, then it is a valid access. Then what you do, you add the displacement with the base address, so that you'll get the actual physical address in the memory. If suppose this displacement is greater than the limit, then what will happen, you'll have a trap or the addressing error. That means your operating system will understand that the CPU is trying to access some other segment's instruction, it is invalid. Okay, so this is how your segmentation hardware works. Fine, next we will see an example here. So as you can see here, this is an example of segmentation. So you can see here, right? This is the logical address space where you have 5 segments. Segment 0 is subroutine. Segment 1 is square root function. Segment 3 is stack. Segment 4 is symbol table. And segment, okay, I missed something. Segment 2 is main program. Okay, this is 0, 1, 2, 3, and 4. Fine. So now in the segment table, how actually your values would be present is, as you can see here, we have 0 through 4 segment numbers, right? So you can see here segment table, it has 0 to 4. That is the segment numbers 0, 1, 2, 3, 4 are the index to your segment table. Now we have to have the limit and the base values, right? So say for example this segment 0. In the main memory, you check where this segment 0 has been stored. So you can see here segment 0 has been stored from the location 1400 and 2400. Fine. Now, how your segment table is updated as, so you can see here 1400 is the base location. Now 2400 is the end location of that particular segment, right? Now you subtract 1400 from 2400. What you get? It is 1000. Now that 1000 is your limit of that particular segment. Let us consider segment 1, square root. Check where segment 1 is present. It is here, right? So the base, what is base? 6300. You can see here 6300 is present, and say the end or the last location of this segment is 6700. So now you subtract 6300 from 6700, so you get the difference of 400. Now that 400 is limit of your segment 1. Okay, so this is how you have to calculate the base and the limit. So now let us see how a particular instruction from this any segment would be taken. Okay, say for example we have this segment 2 here. Okay, right? So say what is the limit of the segment 2? It is 400. That means this entire segment is of 400 bytes long. Okay, now say suppose you want to know the 53rd byte of this segment 2, or you have to know, or CPU wants to execute the 53rd location in this segment 2, then how it can be done? So first you have to have the base of the segment 2. Base address is 4300. Okay, now what you have to do? So as we all know, so the reference to the byte 53. Okay, say suppose 53rd byte the CPU wants to execute. So how this 53 among this from 4300 to 4700 is calculated is like, it is simply the base 4300 plus your the uh, 53rd byte. So like this, so 4353 you will get. So once this is done, the CPU will go to this physical address 4353 and it will start executing again. Whenever this 53 has been generated, right, that has to be that displacement, or yeah, that displacement, it has to be compared with your limit. So limit of segment 2 is 400, right? You can see here, right? Limit of segment 2 is 400 and your 53 is less than 400. Then only what will happen? You can add the displacement with the base. Basically nothing but the same diagram I am explaining. I am taking as a base as this diagram, and I am giving you the particular example, right? So the segment number was 2. I'll explain once again. Segment number was 2, and now we want to say suppose the displacement is 3, right? Now this 53 is first checked with the limit we got as 400, right? It is checked with this one. If this is true, then it is added with the base. In our case it was 4300. Then at the location 4353 your CPU starts executing the instruction. If not, then what will happen? Addressing error or the trap will occur. I'll give you an example for that. Now say suppose say you want to, or your CPU want to access say suppose 1222nd byte in the segment 0. Okay, so this is your segment 0, right? What is the base of segment 0? That is 1400. Okay, now displacement is 1222. Your CPU wants to execute the instruction which is present in 1222nd location. Now you check whether this is less than the limit of the segment 1. What is the limit of segment 1? It is 1000, right? It is 1000. So your displacement is greater than the limit. That time what will happen? A trap would occur. Why? Because your segment is only of 1000 bytes, right? How can you access this 1222nd byte in that particular segment? So that results in a trap. Fine. So this is the example for your segmentation, and this is the last topic in your fourth chapter. Okay, so we have completed the fourth chapter here.